Alright, welcome back to these slides. Let's continue. So we talked about functions last time. Now it's time for this new thing called relations. And it should make enough sense. It's kind of like a more lax function in a sense. It's got some less strict requirements. So a relation is all about formalizing relationships between two sets, not maybe an input-output relation, but something else. Alright, so it's some relationship forms a relation. All right, a binary relation between two sets A and B is again a subset of A cross B, just like a function. A function was a subset. A function from A to B is a subset, a special subset of A cross B. A binary relation on two sets is again a subset of A cross B, and then anything goes for relations. They don't have to don't have to map a single value to some output. It's all just whatever you want to put there. How are they related, essentially? So here is, let's say that I have two sets again, x and y, and just the same as last time when we defined functions, let's say that, I don't know, I've got 3 elements in my domain. And 1, 2, 3, 4, or it's not really even a domain anymore. I've got 3 elements of x. That's what x is, that's the set. And then I've got 4 elements for y. y1, y2, y3, y4. And those are the 2 sets, and there is a relationship between certain elements. Alright? Doesn't matter what that relationship is, I would like to link elements of x to elements of y. That's what a relation does. So let's say that x1 is related to y1. And x1 is also related, and maybe in a different way, to y3. There's no arrow anymore, it's not a function. And then x2 is maybe related to y2 in some certain way. And then let's say that x3 is not related to anybody, and similarly y4 is not related to anybody in x. So these lines make up the relation. It's just saying like x1 is linked somehow with y1. It's also linked somehow with y3. There's no input and output anymore. There's no concept of that. It's just these elements go together somehow. There's a relationship between them. Okay? And so again, it's a subset of A cross B, or x cross y in this case. So you can define it this way. It's just a set of ordered pairs. The relation R is equal to all the sets of things that are related. So A comma B is in R if A is related to B. So x1 comma y1 is in R, because there's a line going between them. x1, y1, it's in R. x1, y3, similarly, also in R. x1, y3. x1 is related to y3 under this relation. And then x2 and y2 are also related. And those are my 3 elements in the relation. All right? So you say that A comma B is in R. That indicates that A is related to B. So x1 is related to y1, x2 is related to y2, and so on. Instead of writing it like this and saying like A and B are related and using set notation, instead of that, we like to say this notation instead. We put the name of the relation in between. We say A, R, B. It's a weird idea, but it's actually going to make a lot of sense, and you will soon see why we do that. Once I show you some symbols that you've already seen before, it's like, oh yeah, those are relations, I get it. So for example, instead of writing x1 comma y1 is in R, we say that x1 is related R. We just say x1 R y1. That's how we can say that idea. Okay? So here is an example relation. Let's make a relation called T, and it's on 2 different kinds of things. So on the left side of T, the thing being related on the left is an element of Z, so an integer, a whole number. And then on the right side, the thing on the right of the relation sign is going to be a real number. So it's relating integers on the left with real numbers on the right, and here's how we can define this relation T. Let's say that x, again an integer, is related to a real number y if x is equal to the floor of doing y plus 0.5 first. All right? So let's write down some elements that are related under T. So what are some elements? And usually, like, we're computing with this side, so maybe we should start saying, like, okay, what is related to what, where we start with the thing on the right, and we kind of end up with the thing on the left, because that's how it's defined. That's an easy way to think about it. There's a computation involved. So, like, 3.14, what's the thing that would go left on the left side of this relation? What is, under the T relation, what is 3.14 related to on the left? Well, you just kind of plug it in. xty if x is equal to y plus 0.5 the floor of that. So the 3.14 plus 0.5 is 3.64. The floor of that is just take it to the smallest whole number, the next smallest whole number, and that is 3. So 3 is related to 3.14 under the t relation. And then what about 5.67? What's that related to under t? Well, you're going to do 5.67 plus 0.5, so that's like 6.1 something, 6.17. And the floor of that, go to the next smaller whole number, and that's going to be 6. And so this relation, t, the relation t is rounding, mathematical rounding to the nearest number. So 3.14 rounds down to t, or rounds down to 3. 5.67 rounds up to 6. And so this is how you can implement the round function if you didn't have one in the standard library, but you did have floor. You could just add 0.5 to your number and then take the floor, and that gives you real mathematical rounding to the nearest whole number. Isn't that cool? So that's a relationship between numbers, a number and its rounded equivalent, a number and its rounded equivalent. That's what a relation can represent. Okay, so hopefully that's making a little bit of sense in your mind. It might be a little bit fuzzy still, that's okay. But let's keep trucking, see if it makes a bit more sense with more examples. So pictures are nice. You can draw a lot of pictures with relations, just like I drew these lines. But you can also represent relations as matrices. So a matrix representation of a relation R is when you put like elements of the left side as like rows, and then you put elements of the right side as columns, and then you put a 1 if they're related, like Lawton and car are related, Lawton and spaceship are related, and a 0 if they're not related. Okay, that's the idea. So a 1 in row R and column C means that the element that represents the row and the element that represents the column are related to each other, and a 0 otherwise. So that's how you can precisely represent some relation. And so let's say that, let's define a relation C on people and objects. So like, here is my set of people. Lawton is a people, and then NASA, let's pretend that corporations are people. I guess they're treated like that under the law anyway. And then objects are going to be the other set in this relation. So here are 3 objects that makes up my object set. So a car, a cat, and a spaceship. All right. So let's define our relation C as P on the left is related to under C and O on the right. So a person is related to an object if that person has that object. Okay? So for example, if you write it in the normal notation that we know from before, I have a car. So that would be in the C relation. Lawton and car would be related under the C relation because I have that thing. And then Lawton and cat are also related because I have a cat, right? And then NASA owns quite a few cars. And then NASA also owns a spaceship, at least one, right? So that would be the relation C. That's what the things are, what those things are that are represented, all right? That's what owns what. So yeah, you could change that into a matrix form is all. You could say like the rows are the people and the columns are the objects, and so you put a 1 if the person owns that thing. So I have a car, so you put a 1 there. Lawton and cat are related, right, under this relation. Lawton and spaceship are not related, so you put a 0 there, indicating that I do not own a spaceship, unfortunately. And then NASA has plenty of cars and spaceships, but I don't think they have any cats. At least they're not doing any experiments on them anymore or something. So I think we're good there, and we can safely conclude that NASA and cat are not related under this relation C. Okay, that's just another example and another way to write how relations work. And I think in your homework, I'll be asking you to use a matrix form as well as this ordered pair form. So now you know. Binary relations are when you have two sets that you're relating, but they don't have to have the same, like the two sets don't have to be the same. Like you're relating some element of set A to some other element of set B. That's totally fine. Like this one I was relating integers and real numbers. You can also have relations, binary relations, on a single set. So you can have a relation that is a subset of A cross A. And what does that mean? You're relating elements of A with other elements of A. That's what that is. That's called a binary relation on a single set. A binary relation on a set A is a subset of A cross A. And in this case, we call A the domain. It's like the one thing. You're relating elements of A to other elements of A. Okay? And because you're doing that, you can now have things called self-loops in your little diagrams, right? Because your elements can be related to themselves. They are of that same set. That's totally possible. And so here is an example, like a binary relation on real numbers. Let's pretend that real numbers is our domain. We're going to create some random relation on real numbers. Like here is a real number x1, here's a real number x2, here's a real number x3. Just pick any random ones in your mind. You can say that x1 is related to itself under this relation. There's no two separate sets to draw anymore. It's you're relating the set elements to itself, to themselves. So x1 could be related to itself, and then x2 can be related to x3. x3 can also be related to x2. That's all possible now because the elements of the domain can be related to each other. It's A cross A, so elements of A relating to other elements of A. All right, so this is called a self loop. It's possible now. x1 can be related to itself. That's totally fine. And then here are some binary relations on single sets that you already know. And this is why we use that in-between notation, like this. Because we use that notation on all these relations. These are relations, aren't they? So the less than relation, that's a subset of R cross R, isn't it? You're saying that two numbers are less than each other, like 2, 3, using this notation. It's in the less than relation, isn't it? And so we write that as 2 is less than 3. We put the relation symbol in the middle. This is why this notation exists, all right? But this is the formal way of saying it. 2, 3. 2 and 3 are related in that order under the less than relation, because 2 is less than 3, all right? You can also define greater than or equal to on real numbers. You can also define it on natural numbers. Like you can say, I'm working with the greater than or equal to symbol for ints, or for whole numbers, for natural numbers only. And so again, you could write that like 5, 2. It's in the greater than or equal to relation. And obviously we don't write it like that. We say that 5 is greater than or equal to 2. We put the relation symbol in the middle. And that's why we do this notation. Okay? You could make an equals sign, equals relation on two sets of things, right? You can relate whole numbers and whole numbers. That's totally fine. And so -2, -2, those are related under the equality relation, aren't they? Because -2 is equal to -2. And so, again, the relation symbol, it's supposed to go in the middle. I hope you understand that the notation looks like this now for arbitrary relations. That's why we write it like that. We're going back to these ideas. Okay? So those are binary relations on a single set, relating elements of a set to elements of that same set. Okay? That allows for self loops. We can now like move around arrows within the set itself. So, okay. Some examples now. Some questions for you to try. So I would like you to try to create the matrix representation for this particular relation. It's a binary relation on a single set. So let's pretend that this is like the set A, right? And the elements are 1, 2, 3, 4. And this is a binary relation on A. A is the domain. So give the matrix representation for it in this diagram, and then also talk about it as a set of ordered pairs, like what's related to what in both this way and this way. Okay, so give that a try for this one, and I'll show you my answer. So with the matrix representation, you are putting on the rows and columns, like the rows become the left side of the relation, so it's all the elements of A. It's A cross A, so elements of A are going to be both the rows and the columns. 1, 2, 3, 4, and then we also have 1, 2, 3, 4 over here as column values. And so again, it's like, is 1 related to 1? You put a 1 there if it is, and a 0 here if it's not. Stuff like that. Okay? So 1 is in fact related to itself, so we are going to put a 1 right here. See that? And then is 1 related to 2, where the left side is the row and the right side, the target of the arrow, is the column, all right? So 1 is related to 1 because there's an arrow coming out of the 1 into a 1. Is there an arrow coming out of the 1 into a 2? There is not. All I see, again, coming out of the 1 is going to the 4. So it's going to be like there was a 0 here, but there's a 1 here. 1 is related to 4 in that direction. And again, there's a 0 with the 3. I hope you see that. Okay? So there is an arrow relationship going on. Like the row represents the source of the arrow, and the column represents the target of the arrow. Okay, that's important. And then 2. Is 2 related to anybody? Is 2 the source of any arrow? Yeah, it's the source of this arrow, where 1 is the target. So 2 is related to 1. So we're going to put a 1 in that location. Then 2 is not related to anything else. It doesn't have an arrow coming out of it going to anywhere else. Just 1. All right? 3. 3 is related to itself. That's cool. So 3, 3, 1. 3, 2 are related as well. So there's an arrow exiting 3 and entering 2. So there's a 1 there. And those are the only 2 things that 3 is related to. And then finally, what is 4 related to? It's only related to 3, because it's the source of the arrow going to 3. So there's a 1 there, and 0s everywhere else. So that would be our matrix form of the relation. And then it's also very easy. Let's pretend that the relation's name is R. It's very easy to express it as a set of ordered pairs. It's just what are the ones? Just pick out the ones in the matrix and write those down. So it's like 1, 1, 1 and 1 are related. 1, 4 are related, in that order, right? It's row to column always. The order is very important for relations. And then 2 is only related to 1, so there's 2, 1 in that order. Okay, it's not 1, 2. And then 3, 3, looks like 3, 2 and 3, 3. 3, 2, 3, 3, and then we got 4, 3. That's the idea. Okay, so yeah, that would be the way I would write that down. Please yell at me if you have any questions about that. But like, there's 1, 2, 3, 4, 5, 6 ones there, and so there's 1, 2, 3, 4, 5, 6 ordered pairs in that representation of the relation. All right. Here are some terms that talk about relations on a single set. They can be reflexive, symmetric, transitive. Those are some new words that we should talk about. So let's pretend that we have some generic relation R on a set A, and here is the idea. R is called a reflexive relation if for every x is related to itself. So for every x in A, x is related to itself under that relation. A reflexive relation has this, okay? So is, for example, it's always good to go back to the relations that you understand, so like less than, equals to, things like that. Is less than a reflexive relation? Is every element related to itself under the less than relation? So like 1 is related to 2, or sorry, is 1 related to 1 under the less than relation? Is 1 less than 1? Question mark? No, it's not. And so R is not reflexive. It's actually, if it's less than, it's anti-reflexive. That's the other way of saying that. So R is anti-reflexive if and only if, for every x in A, XRX is false. X cannot be related to anything, right? So, for example, is 1 less than 1? Question mark? No, 1 is not less than 1, we say. That's the true statement. So it's never true for the less than symbol. It's an anti-reflexive relation. But less than or equal to is totally a reflexive relation, right? 1 is less than or equal to 1. So that's a reflexive relation. Less than by itself, though, is anti-reflexive, all right? And then instead of saying, like, it's not true that x is related to x, a lot of the time you can just draw a slash through the relation symbol. And so this is a common thing, right? Not less than, not equal to, all those ideas. That's a symbol you already understand. So that's reflexivity. It's reflexive if every element is related to itself. It's anti-reflexive if no element is related to itself. So less than and less than or equal to are good examples of that. Symmetric, a relation R is symmetric if and only if for every x and y. If x is related to y, it's also related to x, and vice versa. This is an if and only if relationship. If you have x and y related in this order, you then must have y and x related in that opposite order. That's a symmetric relation, okay? It's do they work out, all right? Can you go the other way? And I'll give you some examples of symmetric relations in a future slide. Don't worry about it right now. It's just, can you flip it? Can you flip the values and have it still work for every time you have it in this direction? Do you also have it in this direction? We'll get there. Anti-symmetric is when that's never true. It's saying, like, if for every x and y, not this is true. If you negate it and think about it long enough. Antisymmetricity, I guess that's how you say it. You have a relation that's antisymmetric if for every pair of values, and you know that like x is related to y and y is related to x, that implies that you must have had the same thing, like x is equal to y. That's the only way, that's what it means to be antisymmetric. Where like this was symmetric is when they're different values. It's antisymmetric if the only way that x is related to y and y is related to x is if x is equal to y. And less than or equal to is another good case of that. It's only equal, you can only flip them if the value is equal. So like 1 less than or equal to 1. You can flip that, but you can't flip 1 less than or equal to 2. It's no longer true. All right. Again, I'll talk about this on future slides, but I just want to give you some quick examples as we start. And then finally, we have transitivity. So a relation R is transitive if and only if. Now you have 3 elements to talk about at once. If for 3 elements of your domain, if you have x related to y and you have y related to z, that means you always have x related to z. Like, so you can hop over. You don't have to use y as the intermediary anymore. It's like these exist. If you have them in that way, that means that you always know that x is related to z. Okay? That's the idea. So it's like if you know that like 1 and 2 are related, and you have also that 2 and 3 are related, transitivity would give you the idea that 1 and 3 are related. You can just hop over on that common middle element. That's saying that's always the case. Okay? So without any further ado, I don't want to confuse you too much with just words. Let me draw stuff. So let's talk about reflexivity and anti-reflexivity. So reflexivity means that every element is related to itself. So like here is my generic relation. Like here are the elements of the domain. Like maybe I have some things related to other things. In order for this relation to be reflexive, every element must be related to itself. So these arrows must exist in my relation. Does that make sense? So, for example, less than or equal to and equality are both reflexive relations because 2 is less than or equal to itself, always. Every element is less than or equal to itself. And then every element is, of course, always equal to itself. It's definitely reflexive when you have equality. Anti-reflexivity means that no element is related to itself. All right? No element at all is related to itself. So less than and greater than are good examples of anti-reflexive relations because 2 is never less than 2. That's never true. 4 is never greater than 4. It's equal to it. It's never related to itself under those relations. So that's reflexivity and anti-reflexivity. Next we have symmetricity and anti-symmetricity. So when you have symmetric relations, those let you swap. So like if x is related to y, then you must also have y related to x. You must always be able to reverse the arrow, all right? Which element comes first makes no difference because you should be able to swap, all right? So essentially, you don't need arrows if you know that it's reflexive, or if you know that it's symmetric, because here's essentially what the relation looks like. If this is my generic relation, it looks like this. Maybe these things are related in this way. Boop, boop. If you know that A is a symmetric relation, that means that the following arrows must exist. If this dot was related to this dot, then it must be the case that this dot is related to this dot in that order now. You better be able to flip the order. That's what symmetric means, all right? You need to be able to go in the opposite direction. If you know that this one's related to this one in this order, then it must also be the case that this one's related to this one in this order. You see that? That's what it means. You better be able to swap them. And then again, like if this one's related to that in that order, you always better have that this one's related to this one in that order, in that opposite order. And so you don't actually need to draw arrows when you know your relation is symmetric. You can just use lines because you know you can go in any direction. You can go any way from one to the other. Okay? Let's see here. So equality is a symmetric relation. So like if you know that x is equal to 2, 2 is also equal to x, you can flip them. It's totally fine. If you have one, you always have the other. Is related to, just on humans, that's also a symmetric relation. So if I am related to my sister is also related to me in that order. You see that? That's how you can think about that. So that's symmetric. Anti-symmetric is when it's never symmetric, kind of like the only way for it for them to be related is if they're equal. All right, so if you have two elements and you can flip their arrows, if you know that their arrows are flipped, then they must have been relating to each other. So that's what anti-symmetric means. Anti-symmetric relations never allow both x and y related and y and x related when x is not equal to y. It's only ever like this one is true, this side is true, or this side is true when they're non-equal. If they're equal, anything goes. It's okay. So here are some examples of anti-symmetric relations. Less than is a good example of an anti-symmetric relation. So if I have two separate numbers that are related under less than, it's never the case, right? It's never the case that the other way works. Like you cannot also have 3 less than 2. You cannot swap them. Like this side is not true, okay? That's the idea. It's anti-symmetric. Is older than is also an anti-symmetric relation. So like, I don't know, I am a brother, I'm 30, and I'm older than my sister, right? I have a sister, she is 28, and this is true, right? The brother is older than the sister under this relation, is older than sister. But it's not true that you can flip them, right? These are two different elements of our domain. It's not also true that sister is older than brother. Sister is younger than the brother. You see that? That is how that works. So you can't flip it. It's only ever one side is true. One or none, all right? Or if they're the same, it's okay to have a self loop. That's what that also is saying, okay? That's symmetric and anti-symmetric. All right, let's keep on trucking with more definitions. Finally, transitivity. It's when you can kind of like hop over something. It's like if you have this and this, you can go straight from the start to the end. So let's talk about that one. So here are transitive relations. Transitive relations allow you to line up two, maybe smaller in a sense, relationships and automatically conclude that a third relationship must also exist. All right, it's saying that if you have x related to y and y related to z, then you immediately know, like, because these are the same, you immediately can hop over and say that x is related to z. Okay? That must also always hold. All right? So let's see here. Pretty much all of our comparisons are transitive relations. So like, here's what that means, like less than. It's a transitive relation because if you have 2 less than 3 and 3 less than 5, of course you can conclude, right, that 2 is less than 5. You can't align them in that order. Do you see how that works? That's transitivity. It's saying if you have this, and they agree here, then you can immediately just say that 2 is less than 5. And that makes some obvious sense, right? That's a transitive relation. I think for the rest of these, you can convince yourself that the relationships are transitive. And then is related to is also a transitive relation. Like if you know, like, I don't know, here's our relationship. If you know, like, that, I don't know, this person is related to this person, and then this person is related to this person, then you automatically know that there is a relationship between the first and the last. Like, this one must also exist for it to be transitive. You see that? I hope that makes enough sense. So, if I am related to my sister and my sister is related to my mom, I am in some way, right, related to my mom. You can always make that jump. That's a transitive relation. So if you have these two arrows, you are forced to, if you're claiming that the relation is transitive, you are forced to be able to make the jump straight from here to here. This arrow must also exist, right? If you just have a dot sitting out here in the wild, it's okay for it to be there. Or just an arrow like this. There's no third thing. Once there's a third thing to be like this, you have to be able to make the gap. You have to be able to jump that gap. So that's the idea of transitivity, all right? Here's a funny meme about that idea. And then also, like, I don't know, another funny example is like is in love with is not a transitive relation. If somebody loves somebody and that second person loves the third person, it's not true that the first person loves the third person, and that just makes for some interesting gossip, right? So that is the idea. So that's transitivity. If you have this and this, you immediately have the first and the last thing related under that relation, whatever it was. Okay? just as a quick, I don't know, what do you call it? As an aside, I guess, to all of this, if you know that your relation is symmetric, so you have symmetricity, and you also know that your relation is transitive, you have transitivity, you have a certain kind of, if you have both of those together, you have a sense of reflexivity as well. It's not complete reflexivity. Let me just call it like a pseudo-reflexivity. In a sense, having symmetricity and transitivity kind of gives you reflexivity for most of your elements in your domain. So for example, if I know that this element is related to that element, if that's all I know, and then I also know, like this is my relation, it's just on these two things, and I have that one arrow. If I also know that this relation is symmetric and transitive, just following the definition of both of those, you can conclude a lot of things, right? If I know that this is a symmetric relation, that means that this one must also be related in this way. You see that? And then now transitivity can kick in. If I know that I can go from here to here, and then from here to here, I should be able to jump the gap and just go straight from the starting point of this arrow to the ending point of this arrow, which is itself. It's a self loop. You see that? And for the same reason, I could start here and move around like this and get another self loop. Do you see how that gives me reflexivity? This creates a reflexive relation. The reason I call it pseudo-reflexivity is because if you have a dot over here by itself, not related to anybody, then nothing really happens. You can't claim that this is also reflexive. That doesn't exist. You need at least one arrow going out of it, and that gives you reflexivity when you have transitivity and symmetricity together. Isn't that cool? So if you have at least one arrow between two elements, and you know that that relation is symmetric and transitive, your hand is forced to know that those elements are related to themselves. So there's a bit of reflexivity going on. If there's always an arrow coming out of every element, like this one doesn't exist, then that guarantees reflexivity. Kind of interesting. So hopefully that's cool to you too. But yeah, that might be helpful one day. Now you know. So with that in mind, let me give you this slide. Let me just show you that slide for a second again. Here are the definitions of these ideas. The page is important. And then I'm going to give you this example with a bunch of relations. So hopefully you've studied this slide now. For each relation below, for A and B, do them both, indicate whether that relation is reflexive, anti-reflexive, or neither. Right? It can only be one of those three options. Symmetric, anti-symmetric, or neither. And then transitive or not transitive. All right, so try all these for both A and B, these relations, and then we'll come back and I'll show you my answers. Okay, so for the first one, for relation A, the domain, the relation is called T. It's a group of people, or relating people to themselves. So X and Y are related in that order under T if person Y is taller than person X. So there's like a less than relationship going on. And you can assume that there are at least two people in the group who are not the same height. Okay, interesting. So first of all, the question is this a reflexive relation? Can it ever be true that person A, I don't know, can it ever be true that person A is taller than themselves? No person is taller than themselves, right? So it's never reflexive for anybody in the domain. So this is an anti-reflexive relationship. Do you see that? This is anti-reflexive. So that hopefully makes enough sense. And now is it symmetric? Like if I know that A and B are related under T, A is taller than, if B is taller than A, do I also know, like is there a way to understand that it's also true that A is taller than B? If B is taller than A, is it also true that A is taller than B? No, that kind of is a less than relationship going on, or a greater than, depending on your order. Like if I know this is like if A is shorter than B or B is taller than A, do I also immediately get that A is taller than B? No, I don't. So again, for every element, it's not symmetric. So it's anti-symmetric. Okay, anti-symmetric. And then finally, is it a transitive relation? If I know that, let's see here, A and B are related, and I know that B and C are related under that relation in this order, can I also conclude that A and C are related? So again, it's like, is B taller than A? If I know that B is taller than A and C is taller than B, can I conclude that C is taller than A? Again, it's like a less than relationship. A is shorter than B and B is shorter than C. Is it true that A is shorter than C? That's another way of saying it. Yes, yeah, that totally makes sense because it's like a less than, and less than is transitive. This is a transitive relation. If I know that C is taller than B and B is taller than A, then of course C is taller than A. It's taller than the person that I knew about, right? So that's why it is anti-reflexive, anti-symmetric, and transitive. It will take a while for these terms to sink into your mind, so do come back to this example if it doesn't make too much sense right now. All right, relation B. The domain for it is Z cross Z, so we have two integers that we're relating. And so let's say that AB is related to CD. Oh, sorry, excuse me. I'm reading it wrong. It's a relation on ordered pairs. So like you're relating ordered pairs to other ordered pairs. Excuse me. So AB, that pair is related to CD under this relation, whatever we call it. We're calling it R or something. If A is less than C and B is less than or equal to D. So A is less than or equal to C and B is less than or equal to D. Let's talk about it. So it's like we're relating A comma B under this relation R to C comma D. That's what the relation looks like. And so the question is, like, is it reflexive, anti-reflexive, or neither? Is it true that AA is related to AA? And so just following the definition. This is true if A is less than C and B is less than D. If you just think about them as like the first thing in the first ordered pair is less than or equal to the first thing in the second ordered pair, and the second thing in the first ordered pair is less than or equal to the second thing in the second ordered pair. It's hard to explain, but yeah, of course. Is this true? Is this true? Of course it's true, because A is less than or equal to A, and A is less than or equal to A. Does that make sense? That's the idea. So it is a reflexive relation, because every ordered pair is related to itself. It's totally fine. And then, all right, is it symmetric? Is it a symmetric relation? Let's see here. Well, it might also help to just have some examples of like what is in this relation. Like if I know that this is true, like if I have 2, 3, what could 2, 3 be related to? Like it could be related to 3, 3, because 2 is less than 3 and 3 is less than 3. That's one element of the relation, right? That's the idea. And so it might help sometimes to think about examples. So that's one example. I think you can think of more. So like 2, 2 is related to 2, 2 under the relation. All right, what about symmetricity? Is it a symmetric relation? If I know that, don't know where I want to write this. If I know that, I don't know, AB is related to, or if I know that AB is related to CD, do I then know, can I prove, do I always have the idea that you can go the other way? Is CD related on the left to AB? And let's see here. If I know this, if I know that AB is related to CD, what do I know about A, B, C, and D? I know that A is less than or equal to C, and B is less than or equal to D. Does that allow me to conclude that C is less than or equal to A, and D is less than or equal to B? That's me flipping these things. That's almost never true for less than or equal to, right? I can never flip them. The only time I can flip these is if they're equal, like this was 2 and 2, and 3 and 3 or something. If it's only possible when it's equal, that screams anti-symmetric, right? You can only flip it when they're equal. So that is an anti-symmetric relation. I hope you see that. And then finally, is it transitive or is it not transitive? So let's see here. If I know that, well, maybe we can use this example. Again, you shouldn't just generalize from examples, but this will give us enough firepower, I think. Let me put it over here. If I know that 2, 3 is related to 3, 3, and then I also know that 3, 3 is related to, let's like section all this off. There we go. If I know that 3, 3 is related to some other thing, I don't know, it's related to 4, 5, because 3 is less than or equal to 4, and 3 is less than or equal to 5, do I then have this one related to this one? I can just skip over the 3, 3. Do I have, like, I don't know, R sideways going from here to here? Do I have that? Is it always true that like, this one is working, right? 2 is less than or equal to 4, and 3 is less than or equal to 5. Can I conclude this always? If you think about it long enough, you can. Because what is this saying? Like, this is saying that 2 is less than or equal to 3, and then 3 is less than or equal to 4. Because less than or equal to on those individual elements is a transitive relation, just doing the same thing twice for ordered pairs, like 3 less than 3 and then 3 less than 5, it gives you transitivity again, right, on the pairs now. So if this is like this and this is like this, you can go straight. You can always conclude, like, yeah, the first thing is less than or equal to this last one's first thing because of the intermediate transitivity of these smaller elements inside of it, okay? If you think about that long enough, you can formalize it. But yes, it is a transitive relation. And I hope this example helps you see why. Okay? You can go sideways. So definitely this is a harder example. Please come back to it. It's a good one to study. Let's see here. Yeah, just a few more examples and terms for the day. This is a fun idea. I'd like to talk to you about a data structure called a graph. It's like a tree, but it's a bit more lax. We'll talk about graphs in detail in a future section, in a future set of slides. But just right now, let's talk about directed graphs, because essentially relations on single elements, they're just a bunch of dots and arrows, and that's all a graph is. So a directed graph, also called digraph for short, so they took the di and shoved it at the start of graph. It's a pair of two things. It's a set of v vertices and e edges. So all you need to make a graph is to know what are the vertices, and then what are the edges that connect the vertices. And obviously that's going to be an ordered pair. It's like this one is connected with this one. This is the source of an arrow. This vertex is the source of an arrow. This is the target of an arrow, right? So yeah, digraphs, as you've seen, they're used to represent relations. They can also represent other things, other ideas, like Google Maps, for example, is under the hood using a graph of all the streets and how they move around. So like, you can talk about roads and cities, like there's a road from Fresno to San Jose, there's a road from San Jose to San Francisco, and you can definitely find a way to get then, therefore, from Fresno all the way to San Francisco and in the opposite places as well, all right? So yeah, it's natural to want to be able to move around a directed graph. It's like, you can think of it as driving or something, or flying. And yeah, moving around draws a path, which makes a lot of sense, like that's a technical term. So there's a path in this directed graph from Fresno to San Jose and Fresno to San Francisco and Fresno to Santa Barbara, Fresno to LA. There's two different ways to get there, two different paths to get from Fresno to LA. That's legitimate mathematics. Those are the technical terms, all right? So for example, if we were to represent this idea of like cities and them being connected by roads or something, we can represent that as a directed graph in this way. You have to say what the vertices are and what the edges are. So the vertices are the places that are like the sources and targets of arrows. Those are the cities. The vertices are like all these cities, San Francisco, San Jose, Fresno, and so on. And then the edges are the things that are relating them. It's what's going between them. So like there's this arrow, right? Fresno to San Jose. So there's going to be that in the edges graph. Fresno to SLO, for example, that's representing this arrow. That's going to be in the edges set. It's a set of ordered pairs. Like this is the source of the arrow, this is the target of the arrow. There's also an arrow from Fresno to LA. That's that arrow. That's what this is representing. Okay? And so there's SLO, Santa Barbara, LA, Fresno, San Jose, San Jose, San Francisco. That's the edges set. Okay? I don't know if that makes enough sense. And then moving around along potentially multiple edges, you can draw paths. So like there's a path from Fresno to Santa Barbara, and it goes through San Luis Obispo. That's how you think about it. All right, so that's hopefully not too bad. It's just an idea that you kind of understand already, just naturally by looking at maps. With that in mind, I think let's keep on trucking. So I think this will help just solidify everything. Let's talk about taking a relation and composing it, because we had function composition. Relations are similar to functions. We can compose those too. So here's how you can think about that. The composition of relations, R and S, on a set A, for example, it's another relation on A, and it looks like this. Let's first do R, then do S. S after R, again, but relational sense, not functional sense. It's a little weird. And so here's how you define it. It's like A comma C. A is related to C under this compose relation, if and only if, you got three elements, there's like some transitivity ideas going on. If and only if like you can run the R relation, if you know that A is related to B, and then you also know that B is related to the C that you're looking for in S. So this is in the relation R and this is in the relation S. You can kind of like squish them together and know that A and C are related. That's relation composition. It's a very transitive idea. You see that? So you work from right to left as usual, and you're running the relation R and then the relation S, and this is saying that A is related to C under the combined relation. If you have this and then this, all right. So it's essentially transitivity. It's saying like here's A, B, and C. A, B, and C, and it's saying if you can find some arrow in R that takes you from A to B, and you can find some arrow in S that takes you from B to C, then you can compose the relations and know that first doing R and then doing S, so S composed with R in that order, this is in this relation. Okay, so it's a very transitive idea, and it will make a lot more sense, I think, with an example. Okay, so let me draw everything out. So let's say that here's my relation. It's going to be A, B, C, and D. Those are the elements of the domains of each of these relations, S and R. And let me use blue to represent the relation S, and I'll use green to represent the relation R. So here's A. Let's put these in space somewhere. Here's A, B, C, and D. Let's use the relation S. Let's draw the relation S. So A is related to B, so source A, target B. There's an arrow in that direction. A is related to C under the S relation. C is related to D under S. And C is related to A under S. Okay? So that is the S relation. Let's do the R relation now. Let's say that green represents the R relation. And R is B related to C. So that's in the R relation. And then C is related to B. So you can do that as well in the R relation. A is related to D, and then D is related to B. So that is the R relation. And so now the question is, what is S composed with R? I'm going to have to redraw the whole idea. So I'm going to use rainbow for the composition. A, B, C, D again. The idea is, like, you start asking the question, like, is A related to B under the composed relation? By doing R first and then S. Is there a way to get from A to B? So it's like, do R first and then S. There's no way in R to get from A to B, right? But there is a way in R to get from A to D, and then if there were also a way to get from D to B in S, then it would be in the composed relation. So it's essentially, the idea of the composition is follow an R arrow, then follow an S arrow. Those are the things that are related under the composition. Follow an R arrow first, then follow an S arrow afterwards. Those are the things that are related. So green arrow, then blue arrow. Okay? So here's me following a green arrow. Now I need to follow a blue arrow to get something that's in the composed relation. There is no blue arrow to follow at D. Do you see that? So there are no things coming out of A in the composed relation. It's impossible. You can't follow a green arrow out of A and then a blue arrow somewhere else. All right, that's what composition of relations means. I hope that makes enough sense. It's a little weird. All right, so that was this arrow. Nothing working there. Let's start from B now. We have a green arrow out of B, a single green arrow out of B. So follow a green arrow in R, and then compose it with S, so follow a blue arrow after that. Are there any blue arrows to follow? Yeah, there's this one. So we could start at B and end up at A in the composed relation. You see that? So B is related to A under the composed relation. Oops. So there is this arrow in the composition. That exists. Likewise, we can still draw this one. We already did that one. That's a blue arrow. We can also follow this blue arrow. And that leads us from B to D. That gives us an arrow from B straight to D in the composed relation. You see that? That's the idea. And so that's how you play the game of relation composition. All right. So let's see here. We've used this green arrow as much as we could. We've used the one from A. What about C? Any green arrows coming out? Yeah, there's this one. So there's that. And are there any blue arrows coming out at B that we could use? I don't see any. So there's nothing coming out of C in the composed relation. That's what we know now. And then finally, what about D? Are there any green arrows coming out of D? Yes, there is one. And are there any blue arrows coming out of B now? No. So again, there's nothing in the composed relation coming out of D. So it looks like in the composed relation, we know that B is related to A and B is related to D. Those are the only things under the S composed with R relation. Okay? That's the idea. If you know that A and B are in R and B and C are in S, then you can conclude that A and C are in their composition relation. All right? That's very similar to function composition. And if that was too confusing, here's an easier way to think about it. Composing a relation with another relation is just finding paths of length 2 where the first one is green and the second one is blue or something. If you're composing a relation with itself, it's even easier. If you compose a relation with itself, it's just find all the length 2 paths that exist in the relation's graph, which makes it very easy. Like here's the length 2 path. Now I know that that is there in the composition. All right, so think of that, and that should be helpful. That's going to lead us into this idea called closure. Okay, so I'm going to give you an example on the next slide. I need to say a lot of words right now, though. All right, a lot of words and terms. Sometimes we have a relation R, and it's a nice enough relation, but it could be better. All right, our relation R, maybe it's not reflexive, it's not symmetric, and it's not transitive. It's like it's missing some of those. And hopefully you've seen by now that like these are things that you might want your relation to have. Like you'd like the relation to be reflexive, symmetric, or transitive. But right now maybe it's not. You can change that relation R to be something more that is reflexive, that is symmetric, that is transitive. And the idea is you don't want to add too many arrows. You want to add just enough arrows to make it reflexive, just enough arrows to R to make it symmetric, okay? So that's the idea. You want to create the smallest relation that's the same as R, but also reflexive, or also symmetric, or also transitive. All right, that's the idea. So when you take your starting relation R and you change it to be blank, symmetric, transitive, whatever, then you have made the blank closure of R. So you can make the reflexive closure, the symmetric closure, or the transitive closure of a relation. All right. And here's how you do it. If you have a relation that's not reflexive yet, just add a self loop to everybody. Add XRX for every X in the domain, okay? For example, the reflexive closure of less than is less than or equal to. If you think about that long enough, that is true. All right, symmetric closure. If you have X related to Y, just add the other arrow. You're forced to have it if it's symmetric. You are forced to add that. And that's the smallest, bigger relation that is also symmetric, all right? Then finally, the transitive closure is if you have X related to Y and Y related to Z, then you better add an arrow. Add that X is related to Z. Keep doing that, because this might add more things that gives you more transitive things to add. You got to keep doing that until there's nothing left. The rest of these are kind of like a one-off thing, but with transitive closure, you might like create an arrow that's going to like kick off a bunch more transitive closure rules that add even more arrows, okay? And then finally, if you think about this in terms of graphs, to do the transitive closure, this will make sense with an example, you are going to add a relation from any element to any other if there is some path to there. You can go straight there. if you have transitive closure. You add x related to y if there is some path from x to y in the original graph of that relation. So that's why we talked about digraphs. Okay, so that's closure, and let me give you some examples of closure, and that'll be the last thing that we do today. So here is the same relation 3 times. I think I stole it from the book or from the internet somewhere. I would like you to first find the reflexive closure of the relation, then the symmetric, then the transitive closure. I think it would help if you tried it, but I'll do it for you. If you are ready, just think about it at least. How do we create the reflexive closure of the relation? We are forced to add x related to x for every element in the domain, if that is not already there. So to make this a reflexive relation, I compute the reflexive closure, I'm adding self-loops to everybody. That's what it means to reflexively close this relation. All right? So that's the reflexive closure. The symmetric closure, also not too bad. It's like, all right, if you have an arrow in this direction, like if you have x related to y, you must add y related to x. So if you have this arrow, you are forced to have this arrow if you're making a symmetric relation. See that? So this arrow implies that you need to make this one. You got to make that one. Got to make that one. Okay, that's the symmetric closure. And yeah, so if you have this one, you always have to be able to flip it. And that's what it means to be symmetric. It must exist. And we're making it if it doesn't already. So that's taking that relation and making it a symmetric one. And then finally, the transitive closure. Let's find the transitive closure of this relation. I can do it from the original example, but it really is easier to think of it in terms of like add an arrow if there is a path. That's going to make it easier in your mind, I think. But just from the rules, like if you have x related to y and y related to z, then if it's transitive, and we're forcing it to be transitive, you better add x related to z. Okay? So here's the idea. I have 1 related to 2 and 2 related to 5. What does that mean? I better be able to go straight from 1 to 5. That's what transitivity means. If this is a transitive relation, I'm trying to make it one, I need to add this arrow. Okay? And this is going to start off more arrows to add. I guess even then, like this one and this one, again, you can compose them in a sense. So 5 is related to 4 and 4 is related to 3. You can go in one big fell swoop from 5 to 3. Transitivity requires that. But we're not done still. Like these new arrows have forced other transitive requirements, using them now. See that? Because like now I have 1 to 5 and then 5 to 4. Now I can go straight from 1 to 4, and I wasn't able to do that before. So that's another arrow I must add to create transitivity, because this arrow is now in the relation. I need to use it. Okay? And so then now I have this arrow straight from 1 to 4, and now I have 4 to 3. Oh shoot, I can go from 1 to 4 and 4 to 3, so I should be able to go, if it's transitive, and I'm trying to make it transitive, all the way from 1 to 3. Whee! There you go. And let's see, did I do them all? I have 2 to 5, and now I added an arrow from 5 to 3, so I should be able to go straight from 2 to 3. See that? Oops. That's the idea. And let me think about all of these. I believe that is all of them. Like, I was about to draw 1 to 4, but I already did it there. So that exists. It's just if there's ever, like, take the original graph, all the paths, like 1 can go to 5, you better add an arrow from 1 to 5. 1 can go to 4, there's some path to get us there, so I better add an arrow from 1 to 4. Same with 2 to 4. That's there. Oh, did I not add that one? Yeah, so that's one that I forgot. Just think about all the paths. 2 to 4. I don't see an arrow there. So that needs to be there, because I can go this one, compose them. That should be transitive. And then, let's see, I have 5 to 4 and 4 to 3, so I should be able to go from 5 to 3. And I believe that's all of them. So that one can go to that one. This one can go to each of these. It's like, because it's a line, it's just one big straight line. It's like this one can go to anybody after it. So this one can go from there to there, or also to there. And then 1 also can go from here to here already, to here, and then all the way. I think, yeah, 1 is related to everybody now in the transitive closure. And I think that I've put all of those there now. Yeah. All right. that to my eyes looks correct, and that is the transitive closure. Notice that when we add some arrows, that forces our hand on other ones, because now we need to use those and force it to be transitive some more. Okay, so that's closure. These are the smallest relations that have the property that we care about. Notice that the reflexive closure did not add me, or did not involve me adding an arrow that looked like this, right? That was useless. That would have made a bigger relation than I needed to make. I want to make the smallest relation, that is, starting from this one, also reflexive, also symmetric, also transitive. Okay, so that's closure. We'll learn a bit later why reflexivity, symmetricity, transitivity is a great idea to have. And so it's useful to want to make these. Just take my word for it for now. That's where I want to stop for the day, though. So let's see here. There is one thing that I want to talk about. We are in week 8 right now, which is about smack dab in the middle of the semester. It's there's 16 weeks of class and then 1 extra week of finals, so we're about in the middle. And so I make this page that I like to give to my students. It's just a Google form. It's completely anonymous. If you have some time, I would really appreciate that you filled it out. Of course, I'll change the due date to something normal. It's not going to be worth any credit. It's completely anonymous. Obviously, I can't link it back to your name or anything. But I would appreciate you giving me some feedback on the class at this point. While there's still time to, like, if something is going horribly wrong in your mind, please tell me about it so I have some time to make things better while you're still in the class. And this will help me improve the class, of course, in future semesters as well. So I would appreciate your feedback, completely anonymous. And yeah, just click the link and fill it out if you can. And I think that is everything that I wanted to talk about today. There's still a few extra slides here. We'll get to those next time. So I'll see you next week.